Welcome to this short recorded lecture, the third lecture for Math 5027. So this one is on convergent sequences and subsequences in a metric space. Again, I'm following some of the book's notation, so it's M. You'll occasionally see things I'm writing involving a metric space X, but outside of notation for what the space is, there's a lot of good stuff to read here. I do prefer this notation for a sequence, just using parentheses around a p sub n, points p sub n. I'll often use x, little x sub n for mine. This notation with the curly brackets is not advisable because I think it gets confused with a sequence or with a set of points from a metric space, an ordered countable set of points. So don't necessarily recommend the curly brackets. They're generally used for sets in a metric space. And if it's got a subscript like an n or an m or a k, then usually you're talking about some countable or finite index set. So this is usually what I use for, not even that one. This is my shorthand usually for a sequence. I just use parentheses, and it's understood that I mean you're indexing from 1, 2, 3, 4. If there's some other indexing that's being used other than the standard natural numbers of 1, 2, 3, 4, and so on, then I'll usually be quite explicit about what that is, or it should be clear from context. There's some great stuff to read here. Again, I'm not going to read everything to you. I think a very important concept that you should get is that a sequence is a function. And it's a function from the natural numbers into the metric space, meaning that the nth term in your sequence is just some point in your metric space. And if you conceptualize it that way, then you might consider actually how to graph it. So I'll choose kind of a big thing here. I'll just write over the text. But you imagine that you could have like your real number line, and this consider like 1, 2, 3, 4, 5, 6. That might be a little hard to see. I know it's kind of messy. And this is your real number line, and you're considering the subset of natural numbers that are a subset of the reals. And then on the vertical axis, it's like your metric space in the book's notation M, or I might use like a capital X. And then every point here is just mapping to something here, so into this space. And that's just a conceptualization of it. It's not to say that our metric spaces are always the reals. It's just a useful way to conceptualize a sequence. It's just a mapping from the natural numbers into points in the metric space. So then we ask questions involving the limits of sequences, if they happen to exist, meaning does the sequence converge to something? So that's this definition that I've outlined in blue here on the screen. So I'll just highlight it here in cyan just in case it's clear, because I know there's kind of a lot going on here. But this part right here is the definition. And I have a whole bunch of stuff that says, how do you parse out the definition and write a good proof? And you should read through all of this in the notes. I'm not going to read this to you. I'm going to go straight to the take-home message, which is actually found on page 3. That involves what's the proof structure. You're going to let epsilon be greater than 0. You're going to choose a capital N somehow, usually through reverse engineering, basically, and you're going to perform scratch work a lot of times where you're going to know this is what you're wanting to show that a sequence of points Pn converges to some other point P in a metric space. You do scratch work involving that. If it's not exactly obvious how to choose the capital N, then you figure it out through your scratch work. You describe how you choose the N here. Then you just write let n be greater than or equal to capital N, and then you show basically what you already know to be true from your scratch work. And that's how you're going to write a nice clean proof. So the example from the reals, prove that 1 over n converges to 0, one of the simplest sequences that you first study in elementary analysis. So here's the structure. I let epsilon be greater than 0, right? Step 1 of my proof. I'm just being very explicit about the steps here. You don't have to write that, and I don't necessarily recommend you do, but I'm just showing these 4 steps. This pattern of the proof is always there regardless of the details. And basically the details for step 1 and 3 are always the same. You're always going to write those 2 things for steps 1 and 3. Let epsilon be greater than 0 and let little n be greater than or equal to capital N. Then where the details change are in step 2, which you figure out by doing scratch work usually involving step 4. So here I just happen to know, like, if it was kind of clear to me, but if it's not clear, you would start with like, look, I need to show that the metric on R, which is just the absolute value of 1 over n minus 0 for the distance between 1 over n and 0, those are my points. I know that I need to make that less than epsilon. And if you work it out, then you'd say, well, 1 over n minus 0 in absolute value is just 1 over n. And 1 over n is less than or equal to 1 over capital N because you're going to choose little n's to be greater than or equal to capital N. So that relationship then gets figured out in your scratch work right there. And then you'd say, well, then how do I choose the capital N to make 1 over n less than epsilon? Well, you just do some algebra, move things around in inequalities, and you realize you have to choose capital N greater than 1 over epsilon. So very simple problem. I showed the details on a different example. 3n over 2n plus 1 converges to 3 halves. So a little bit more complicated. So I show the scratch work. The metric in this case, so in case this is not clear, what I'm saying is that this right here is the metric on the reals, and I'm taking the distance between the point on the reals, 3n over, not 3, 3n over 2n plus 1, and the point 3 halves. It just so happens that on the reals, that metric is given by the absolute value of 3n over 2n plus 1 minus 3 halves. All right. So all I'm doing is dealing with the details of the specific metric space that I have. And I say, I need to make this thing less than epsilon somehow. So I first simplify. I go through scratch work to figure out kind of what this is. And I get to some point like here. And then I do simplifications. And I do a relationship between little n and capital N to create a simpler relationship between capital N and epsilon. And then once I figure that out, I go, okay, time to write a formal proof. Step 1, 2, 3, and 4, always the same steps. I let epsilon be greater than 0. I let little n be greater than or equal to capital N in steps 1 and 3, right? Nothing's changing ever in those steps. And then I got to choose n somehow. The details have now changed for the specifics of this problem based on my scratch work. And it's kind of, you're basically making a fortuitous choice on this based on your scratch work so that step 4 all works out down here. And you just see it like it's kind of a cleaner version of what you do in some scratch work. That's all I'm doing in step 4. So I suggest you kind of go through that same process, do some scratch work, figure this out, write out a formal proof for this. That's some work you should do on your own before class. One thing that I show here is, hey, let script C on 0, 1 be the space of continuous real valued functions on 0, 1. And recall this metric that we've seen now in class that's based on the integral. The distance between two continuous real valued functions on a closed bounded domain can be defined by an integral of the absolute value of the difference. And so one of the things I show in some scratch work and then this proof, here's step 1, 2, 3, look at 1 and 3, 1 and 3, they're the same. And then I just basically show, you know what? In this metric, the function x to the n converges to 0 on the interval 0, 1. And I just going through these steps, and you can read through them. But what I ask you to do is show you, if you use a different metric on the space, the same sequence might not converge. And in fact, it doesn't here. And I give you a hint about doing a logical negation on the definition of convergence of a sequence. So this basic hint, you should go look at the definition of convergence given on page 1 of these notes. I'm just doing a logical negation. And then that means for alls become there exist become for alls, and then the conclusion changes. That's it. So there's 3 logical quantifiers in this. So there's this change, and then this change in terms of for alls changing to there exists, and then the conclusion changes. That's all that goes on when you do a logical negation. And then I say, oh, well, if I have a for all and I write let and I have a there exists, there's a choose. Now you have to choose an epsilon somehow so that no matter which capital N you happen to consider, you let n be any natural number, but whatever one's then chosen, you say, here's now how I choose a little n greater than or equal to capital N such that I make the distance between Pn and P greater than or equal to epsilon. All right, so those are I give you the hint of the structure of the proof. It's still 4 steps. It's just you're interchanging chooses with lets and let's with chooses, and then your scratch work is going to be based on that. You should hopefully figure that out. So work the details out for that problem. And then this is a really useful result, really useful conceptualization of what it means for convergence on a metric space. So if xn converges to x in the metric space x, so here I'm using my notation for metric spaces, which is more common, involving like capital X and little x's for points. This is true if and only if d of xn converges to 0. The distance between xn and x converges to 0. Now, the way to think about that is the sequence xn and the point x, these are points in a metric space. All right? As soon as you take the distance from xn to x, for each n, you're constructing a sequence of real numbers, non-negative real numbers. And then what this means, this is something, really make sure you understand this statement, that this and like that the sequence xn and the sequence the distance from xn to x are different sequences. This is in the metric space x. This is in the space of the reals, regardless of what the space X is. If the space X is functions, sequences, whatever, the distance from X into X is always a sequence of real numbers, right? Even if the sequence of Xn is a sequence of very complicated objects in some strange metric space. So I show you on this video, this is something for you to fill in as the reverse direction. This is an if and only if proof. I'm showing that how you prove this the first direction. The implication that if you have the convergence of X into X, then that means that the distance from Xn to X has to converge to 0 in the reals. So the way I go about that, when I have this forward direction, I'm indicating that part of it in the proof here, is that I say, look, let Xn converge to X and X. I'm just considering an arbitrary convergence sequence in the metric space. And now I need to show, if you think about what I need to show on this forward direction, is you need to show that the distance from Xn to X converges to 0 in the reals. Well, look, here's step 1. Let epsilon be greater than 0. Here's step 2. I have to choose capital N. Here's step 3. I let little n be greater than or equal to capital N. And then here's step 4. All on here is showing why the distance between Xn and X and 0 in the reals is less than epsilon, right? Y converges to 0. So you might have to sit a little bit with this and digest it and make it seem like I'm not writing the same thing just in different ways. These are different objects, different sequences. Xn is a sequence in the space X. D of Xn X defines a sequence of real numbers. So sit with this. It might seem so trivial, but it's not. It's straightforward, but not trivial. Students should work on the reverse direction, meaning assume the distance from X into X converges to 0 in the reals. Show that that means that Xn converges to X. And then I suggest you prove the limits of convergent sequences are unique. Here's an idea. This is not quite a formal proof, but it's basically giving away the idea of it. Let Xn converge to X, and suppose it also converges to Y. And then use a triangle inequality from the metric space that the distance from X to Y is less than or equal to the distance from X to Xn plus the distance from Xn to Y for every single n, no matter which Xn you picked. That just follows from the triangle inequality. Now, by the previous problem, this converges to 0 as in the sequence of reals. This converges to 0 in the sequence of, or as a sequence in the reals, I should say. And by elementary analysis, if you do the term by term sum of two convergent sequences, then that term by term sum converges to the sum of the limits. So that converges to 0. So that's the elementary analysis result. So I'm combining the previous problem with the result from elementary analysis. So if that didn't sound so right in words, what I mean is this: if you have a sequence Sn, I'll write it out a little differently. I'm sorry. So I'll write, if Sn converges to S in the reals and Tn converges to T in the reals, then the sequence defined term by term as Sn plus Tn converges to S plus T. And I'm just using that sequence and that sequence, the distance from X to Xn and the distance from Xn to Y, are two sequences of real numbers that both converge to 0. That's the previous problem, and then I'm combining it with this result from elementary analysis. So then, based on the property of metrics, I know that this distance from X to Y is greater than or equal to 0, and now I've just proven it's also less than or equal to 0. So what is a number that's greater than or equal to 0 and less than or equal to 0? 0. I think you can finish it off from there using, again, properties of metrics. So that's it for this video. Thanks for listening, and I'll be talking to you in the video for Lecture 4.